We'll now look at some simple examples and some simple criteria for continuity. Okay, mixed up. Of course, we'll be looking at examples and criteria throughout this course since they are quite central. But first of all, if X is a space, so let's say example, first of all, if X is a space and I look at the identity function 1x, x to x, which is of course defined as 1x will map x to x, is continuous. And the proof of this is that V in X open implies that what is 1x inverse of V? Well, that's V itself is open in X. So it's trivial that identity is. Any structure is preserved by the identity. The fact that this is a structure tells you that we get an open, that identity is continuous. Okay. Some slightly harder example, but not hard at all. And again, something you want for all structure preserving is that if I have two functions, f and g, and I look at the composition, if each one of them are continuous, then the composition is continuous. So if f from x to y and g from y to z are continuous, so is g composed with f. This is going to be the map from x to z. Well, proof is quite straightforward. If V contained in Z is open, then because f is continuous, then f inverse of V contained in Y is open. This is because, of course, f is continuous, as f is continuous. And now we are taking again the inverse image of a open set, which implies that G inverse of f inverse of V, that is the same as G composed with f inverse of V. So this contained in X is open. That's all. So we have noted that identities are open and constant compositions are open. Another class of functions that's automatically open are automatically continuous are constant functions, okay, which again you would expect by sanity. If f from x to y is a constant function, let's say f of x is identically y naught, then f is continuous. So all these are without any reference to what specific space we are talking about. So, well, how do we know this? If we have f of x is identically y, okay, so let V contained in y be open. What is the inverse image? Then if I look at f inverse of V, there are two possibilities. Either V contains y naught or it doesn't. And if it contains y naught, this is x. If y naught is in V, and it's empty otherwise. And both these are axiomatically open. Hence f inverse of V is open. As you see, we are steadily using axioms of topological space when we do all these things. So another important example which illustrates definition is, so let A contain in X be a subspace. When we say this henceforth, we mean that it's a subset and with a subspace topology, and we have the following proposition. If I look at the inclusion map from A to X, I or iota from A to X is continuous. And as I said, this illustrates the definition. So let V contained in X be open. Then the inverse image under the inclusion map of V is just the intersection of V with A. It's the under an inclusion map, the inverse image of a set is exactly those points that are already in A. So this is open. That is the definition of the subspace topology. Or rather, that's half the definition of the subspace topology. So subspace topology says such sets are open and only such sets are open. We will come back to this later. So when we focus more on universal properties, our focus right now is on simple examples. Okay, and here are a couple of more simple examples. So let X be a discrete topological space, which means a topological space with discrete topology. Proposition: whatever y is, f from x to y is continuous for all y and for all f. Well, this is because the inverse image. So let V in y be open. Then f inverse of V contained in X is open, as every set is a subset is open. Yeah, so it's a discrete topology. So discrete topology tells you nothing by functions from that topology. To that topology, we'll tell you quite a lot. You've already in some sense seen examples in one of the quizzes. But on the other hand, so now if we have an indiscrete topology, be indiscrete, an indiscrete topological space. And then we have the following proposition, that f from x to y is continuous for all spaces x and functions f from x to y. So in the previous case, it was because it was far too easy to be a function open set in X. This time it's because there are far too few open sets in Y. So V in Y open implies that V is V, not Y. V is phi, or it's the empty set, or V is Y, which implies that, of course, F inverse of V in the first case is empty, or F inverse of V is X, which implies that F inverse of V is open. Okay, so this disposed of some rather simple examples. We'll look at a slightly less trivial examples for which we'll look at, actually we'll look at a proposition, a criterion, which will come example, for which we need a couple of modified criteria for continuity. In fact, we need only one, but we will state a couple of other similar ones. So we'll state as a single theorem a few modified criteria. So in all cases, f max from x to y. So f is continuous if and only if for all a in y closed, f inverse of a is closed. So this will turn out sometimes to be the more easy to check or the more easy to use, depending on whether your continuity is your hypothesis or your conclusion. Okay, and again, f is continuous if and only if a couple of other conditions. F is continuous if and only if for all W in Y basic open set, F inverse of W is open. And here, for all W in Y sub-basic open set, F inverse of W is open. Okay, I should clarify and emphasize, being a basic set is not a property of the topology. What I mean is that there is a fixed basis, so that this is true for all sets in that basis. There is a fixed sub-basis for which this is true. That's given to you. It happens. So for B and C, one way is clear, because basic open sets are open. and subbasic open sets are open. So if f is continuous, f inverse of w has to be open. It's the other way, which is a theorem. Okay. But for the first one, it goes both ways, and it's actually quite easy. What is common with all these is they involve those nice properties about inverse image of a set under a function. Okay, so suppose f is continuous. And then A in Y closed. This implies that f inverse, first the complement is open, implies y minus a is open, so which implies that f inverse of y minus a is open, which implies, well, f inverse of y minus a is x minus f inverse of a is open, which implies that f inverse of a is closed. And the converse is very similar. Conversely, suppose we have this hypothesis. Okay, so conversely, let v and y be open. Then, of course, we know that y minus v is closed. And conversely, if we have assumed the hypothesis, which implies that f inverse of y minus v is closed, this time I'll just write this as x minus f inverse of v, which implies that v is open. Okay, so we have seen this in detail. B, so one side is clear. If f inverse of w is open, I'll only write the non-trivial side, and C will skip entirely because it's very similar to B, is open for all basic open sets, that means for a fixed basis, and V is open, then what do we know? Then V is union for some collection, I in I, Wi basic open. So this implies that f inverse of V is f inverse of union of I in I of Wi. But this is the union I in I of f inverse of Wi. And now we know that this is open, and the union of open sets is open, so which is open. Okay. So because of the nice set theoretic properties, any open set is the union of open sets, so we can pull it back. Again, warning, don't try to use this with push forward. Push forward is, okay, it's well behaved with union, so you can with care, but not with complements and not with intersections. So C will also fail. C implies, so B implies C is like B with finite intersections. So we have assumed that suppose we have established B, and I know the inverse image of a subbasic set is open. I'll conclude that the inverse image of a basic open set is open, where the basis comes from the subbasis by finite intersections. And the proof of this is clearly we take finite the same as that of B, except that your basic open set is a finite intersection. So inverse image is a finite intersection of inverse images of open sets, and in finite intersections of open sets is open. So I've just said it verbally. It's more or less the same proof as before. Okay, so that aside, now let's look at an example here. Okay, so proposition. So let X be indiscrete. And F from X to R continuous. So we know some functions from X to R. which are continuous, namely constant functions. There are always constant functions are always continuous. If the target was indiscrete, then any function is continuous. So we have lots of continuous functions, so we can't say anything about them. I mean, everything is continuous in that case. But if the domain is, I mean, the codomain is nice enough, I've specialized to R, but you'll see we use a very mild property of R. And we'll then any function from an indiscrete space is continuous, is constant. Sorry, I didn't write the conclusion. Then f is constant. Okay, so let's just assume it's non-empty. Okay, so proof. So let y belong to f of x, the image of x. So since x is not empty, this is some point in the image. Its image is non-empty, it has some point in it. So what we have to show is every point goes to that. Okay, so then y is closed. Because with real numbers, a single point is closed since its complement is the union of two segments, which are in turn union of open intervals. So then y is closed. Therefore, f inverse of y, this is contained in x, is closed. Okay, but y belongs to, if y is in the image, this implies that f inverse of y is not empty. Okay, I could have picked an x and looked at its image if that's easier to understand. So pick an x, I look at its image, its inverse image contains that x we picked, and so it's non-empty. But indiscrete topology has very few open sets and hence very few closed sets. So if the open set is not empty, so this implies that f inverse of y has to be all of x. That is, for all x in x, f of x equals y. Well, f of x belongs to y, that is f of x equals y for all x in x. So this is exactly what is a constant function. Okay, so this illustrates that from discrete space we have lots and lots of constant functions. As I said, two discrete space will be quite restrictive. We can't exactly state what that is. To indiscrete space we have lots and lots of functions, but from indiscrete space, if the target is, for example, real numbers, every function is constant. In fact, so remark, the above holds in exactly the same proof for all y with the following property. So definition, we'll say that a space, I'll call it y here, is T1 if every point in y is closed. So every point in y is closed. That means it's closed as a singleton set. This is one of the separation properties we'll see in detail, but it came up naturally. So from an indiscrete space, you can't say all functions are constant, because if the target is indiscrete, for example, then we will every function will be continuous. So you can't say continuous functions are constant. But as long as points are closed, which will be true for any metric space, for example, and even certain things which we'll see cannot be metric spaces, like the cofinite topology, as long as points are closed, we have that any continuous function is constant. Okay. So we've seen a bunch of sort of abstract general examples. We've also seen concrete examples in a sense, because we have looked at functions too between metric spaces, and then we saw the epsilon delta definition holds. Okay, we will build further on this as we go along.